Welcome to Chapter 4. We are discussing Newton's laws of motion with this video. So in physics, when we talk about dynamics, we're discussing why things move. And usually we say something moves because of some sort of push or pull. That's a loose definition of what a force is. Normally in physics, we'll define force with an equation. But if someone wanted it in words, you'd say, oh, it's a push or a pull. So objects fall because they're under the force of gravity. Gravity is the force pulling them down. Just because a force exists, you don't always have motion. I could stand and push against the wall in the classroom, and the wall's not going to move. But on some sort of microscopic level, I'm sure there's some sort of molecular motion going on. But I'm not moving the wall. So just because you push on it doesn't make it move. Force is a vector. That means it has magnitude and direction. So we care about how big is it and which way does it point. We will always indicate the direction. By now you should be comfortable with that idea. All right, so Newton's laws. Newton has 3 laws of motion. His first law says that a body at rest stays at rest, one in motion stays in motion, unless acted on by a non-zero net force. Normally in physics, we expect you to know Newton's 3 laws. So if I ask you to state Newton's first law, it would be sufficient for you to say a body at rest stays at rest, one in motion stays in motion. That's not technically as detailed as we would like, but I would accept it on a quiz. One of the many examples used to illustrate Newton's first law is the coin and the index card. So if you have a glass or a beaker or some sort of heavy container, you don't want it super lightweight. So maybe you could do it with a plastic cup. I don't know, it would depend. And you place an index card on top of it. And then on top of the index card, you place a coin, preferably something relatively heavy, so maybe a quarter. If you use your finger, like in the diagram, to flick at the card, the index card doesn't weigh very much compared to the coin, and so the index card is going to fly out, but the coin usually will fall straight down because it's so heavy. So the card moves because you flick it, but the coin is really heavy and it resists moving, and it's sufficiently heavy that instead of moving with the card, it falls straight down because gravity pulls it down. All right, enough of that. We will look at some other examples, and probably I'll try to do the egg and the pie pan demo either in lab or in class when we have our in-person meetings. So the net force is the vector sum of all the forces acting on an object. In order to look at all those forces, we will typically draw something called a free body diagram. We'll start using them in this chapter, but I want you to start with understanding that on a free body diagram, the only thing you show is the object, usually the surface it's resting on, and all the vectors acting on it. So normally all the forces acting on it. I guess it's really all the forces. Free body diagrams show forces. So inertia is the property of an object or a body that forces it to obey Newton's first law. I know that's a terrible definition. I completely understand. Large, massive objects have more inertia than small, lightweight objects do, but mass and inertia are not exactly the same thing, not from a physicist's perspective. We will use the term inertia when we talk about rotating objects. We'll come back to that again. So mass is not the same thing as inertia. Mass is not the same thing as weight. Weight depends on your location. So my weight in Hickory is not the same as my weight on the moon. If you take me to the moon and try to weigh me, I'm not going to weigh the same. And in fact, we have a little example where we will show the differences in the two. So mass depends on you or the object. Weight depends on the location. So, and inertia is related to the mass, but it is not the same thing as the mass. And here you can see in bright red, the egg and pie pan and the bottle and the tablecloth, and we will do those either in lab or in the one day a week we have lecture. So look for those to come. All right, brings us on to Newton's second law. So Newton's first law was a body at rest stays at rest, one in motion stays in motion. Newton's second law summarized is F equals ma. So if I ask you to state Newton's second law, if you just wrote down the equation F equals m multiplied by a, I would be happy. F is the force, it is measured in newtons. M is the mass, it would be in kilograms. A is the acceleration in meters per second squared. So you can have, in this illustration, what they're trying to show you is that you can have two forces that are identical, even though the masses and the accelerations are different. So in the first one, you have an individual hitting a golf ball. So the mass is small, that's the golf ball, but the acceleration is really large, so the force is this middle-sized value. If, on the other hand, you have the golf ball in the truck, and instead of hitting the golf ball, you're hitting the truck apparently, you are going to have a really large mass, that's the truck, and a really small acceleration because you can hit the truck all day with your golf club and it's probably not going to move very much, if at all. So mass can be large, acceleration can be large, it doesn't really matter. Force is mass multiplied by acceleration. But what does matter is that you remember force is measured in newtons as long as we're in MKS units. The CGS units, and we will never use those to calculate force, but if you saw it in an old table someplace, the CGS units for force are dynes, D-Y-N-E-S. So 1 dyne is 1 gram multiplied by a centimeter divided by a second squared. The British unit for force is the pound. We measure force in pounds in the British system, and I expect you to know that. Why? Because we use British units in our daily life. If somebody says, how much do you weigh? You're going to give it to them in pounds. You will not be giving it to them in some other unit. So 1 pound is 1 slug foot per second squared. I think it's interesting in the British system that we measure mass in slugs and force in pounds. So I expect you to know the British unit of force is the pound. I expect you to know the MKS unit, the metric unit for force is the Newton. Notice we abbreviate Newton with a capital N. We abbreviate Newton with a capital N. And I do have a 1 Newton apple that I will try to remember to pass around so you have some sense of it. So weight is the force of gravity acting on an object. You are weighed down because gravity is pulling you down. So remember I said weight is dependent on your location. That's because gravity depends on your location. The acceleration due to gravity at sea level is not the same thing as the acceleration due to gravity on the top of Mount Everest. And the acceleration due to gravity on sea level on the surface of the Earth is not the same as the acceleration due to gravity on the moon or on Mercury or on Venus or on Neptune. All the planets have different gravitational attractive forces associated with them. But if they don't tell you, and we're on Earth, you can assume that G is going to be 9.8 meters per second squared for us. So acceleration with gravity varies, and that means the weight's going to vary, but your mass is going to stay the same. So if my mass is 50 kilograms, but my weight on the moon, my mass would still be 50 kilograms, but my weight on those two locations would be different. All right, let's move along. Enough of that. So let's do an example. A student has a mass of 75 kilograms. We want to know what's its weight on Earth and what would the student's weight be on the moon. So what we are doing is taking a mass. Remember, kilograms gives us the mass, but we want to calculate the weight. Kilograms will give us the mass. So we know the mass is 75 kilograms. We know G on the Earth is 9.8 meters per second squared. We know G on the moon is 1.6 meters per second squared. We're trying to find the weight in those two locations, and we know that weight is mass times gravity. This is the same as F equals ma. Here is the m, our a is little g. Weight is equal to mass multiplied by the acceleration due to gravity. So we'll do it on the Earth. So part one, on the Earth, we write down our formula, W equals mg. We plug in. W equals, well, m was 75 kilograms, g was 9.8 meters per second squared. You multiply those two, you get 735 newtons. On the moon, we write down the formula. It does not matter that you just wrote it down in the step above. Every time you use a formula, you have to write it down. The W equals mg. The W equals, m is still 75 kilograms, but g is now 1.6 meters per second squared. So 75 times 1.6 gives us 120 newtons. You can see there's a big difference in the weight on the moon as compared to on Earth, but the mass is the same. All right, rolling right along. Let's get to Newton's third law. So we've had Newton's first law, just to recap. That was for body at rest stays at rest, one in motion stays in motion. We've had Newton's second law, F equals ma, force is equal to mass times acceleration. Now we have Newton's third law. Newton's third law is that for every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. So a typical example is to put a book on a table. Gravity is pulling the book down. That's the weight of the book. But the table is supporting the book. That's why the book sits still. So the weight pulling down is balanced by the table pulling up. If we were going to draw this as a free body diagram, this little blue box with the little wavy lines in it represents my book. And I have two vectors, one going up, and that is the table pushing up on it, and we call that the normal force. We call that the normal force. I'm going to introduce it later, but for now I wanted to include it. That is the normal force. So this vertical arrow pointing up is the normal force. The one coming down, the blue arrow, is the weight. So for us, that will be little w. That will be little w. I'm sorry about that. There we go. I can hopefully make it go away. So the normal force is going up. That's F sub n. The W is coming down. Normally, I'd write these a little closer to the arrows. And I might also include a line to represent my surface. I chose not to in this, but maybe we should have. So insert shapes. Let's do a line. Maybe I can do a line. Not a very good one, but it's okay. Why did I need to include the surface? Well, usually you want to know, is it flat or is it tilted? And you can't have a normal force unless an object is resting on a surface. We'll come back to that. All right, let's move along. So we said for every action, there's an equal and opposite reaction. Let's look at others. So if you're running on the beach, you push down and back on the sand, and the beach pushes up and forward on you. So you're doing the little blue arrows down and back. The sand is doing the little orangish colored ones up and forward. If you've ever been for a run on the beach and you've looked at what your footprints leave behind, you can see the little divots and the sand throwing out behind you. Another example is getting off a boat. I always hated this part. So if you've got a boat and it's not tied up securely to a dock, normally you would want it tied up both at the front and the back of the boat. The minute you step to get off the boat moves. That's because the water is not a rigid surface. So if you, to get off the boat, you want to go up and forward. The boat, in order to do that, for the boat to push you up, you push down on the boat. So you push down on the boat pushes up on you. You push back on the boat pushes you forward. If the boat were firmly attached to the dock, this would not be a problem. If the boat were on dry land, this would not be a problem. But if the boat is free to move and on the water, the minute you step to get off, you will discover the boat is now farther away from the dock and lower in the water. And for many of us, that makes us uncomfortable. I hate when that happens. Another example, for every action, there's an equal and opposite reaction. If we had you on some sort of skateboard, or actually, I think this is a moving dolly, sitting there, and you are holding probably a medicine ball, so it's big and heavy. If you throw the ball and the ball moves away from you, you will actually begin to roll backwards, assuming the ball is sufficiently heavy and the wheels on the cart turn easily and you don't weigh 40 zillion pounds. All right, let's talk about the normal force, tension, and other examples. So in this, we will discuss the normal force. I've already introduced it. It's a force that is present when you have an object resting on a surface. So that makes it a contact force. Contact forces are forces that result when two surfaces touch. A contact force results when two surfaces touch. And maybe I should put that. Even two objects touch. Sorry, I was thinking of something else. So you have to have touching for a contact force. So the normal force is a contact force, and it is at right angles to the surface of contact. We are going to use F sub n as the notation for normal force. Your book likes to use capital N. I'm sure some of you understand why I don't want to use capital N. We already use capital N to represent the Newton. So I don't want it too many letters to be used both as a variable and as a unit of measure. We are going to use it capital N for newtons. We're going to use F sub n for the normal force. Tension is the force in a rope or a string or something of that nature, and it is going to be symbolized by capital T. Later on, we'll use capital T for something else, but for now, it's going to symbolize tension in a rope. So let's look at these three examples. In which case does the entire effort of the push or the pull go into the motion? So if you pull up on an object and to the right, up and to the right, I've got little hidden boxes here. So let's remove them. What we'll see if I take that force and turn it into the hypotenuse of a right triangle, so in essence resolve it into components. If this black arrow is our force, we're pulling up and to the right. The red or the orange arrow is the horizontal force, and the blue is the vertical. So horizontal force is to the right, blue is coming up. Suppose we look at pushing down on an object. If we push down on an object, our horizontal force is to the right, if we go by the black arrow, but the vertical arrow is going down. So pulling the vertical arrow is up, pushing the vertical arrow is down. Both instances can move an object across the room. If you push down, you're more likely to scratch the floor. And if all three black arrows are exactly the same, the horizontal push-or-pull is the one that's going to utilize every bit of your effort into moving the object. In class, I normally talk about having watched a strongman competition on television one time where grown men were pulling buses using their teeth. They had a chain connected to the bus and a mouth guard in their mouth, and they were pulling. And what I found interesting is they all leaned over so that the chain was parallel to the ground, so that all the effort of their push or pull was like the third example, C, and it went into moving it. In the first two examples, some of your effort is used to either lift up or push down on the object, not to move it horizontally. So there's some homework problems to look at, and there will be study guide questions that were assigned in the chapter assignment. So let's talk about riding in an elevator. In an elevator, as you move up, the floor starts to move a fraction of a second before you do. Especially on older elevators, you notice this. I don't know that you feel it so much on new ones because they have a gradual start up and a gradual slow down. Old elevators tend to just jerk into motion. So this gives you just enough time to exert, it gives the elevator just enough time to exert a push or pull on the bottom of your feet, and you actually sense it or feel it. When an elevator starts to go up, you will have the sensation just momentarily that you're heavy. And that's because the bottom of your feet experience an increased force. Not only the elevator pushing up on you because of gravity, but the elevator pushing up on you because it is now accelerating. It is now moving. So you have two forces, the movement of the elevator up and gravity resulting in the elevator having to support you. When you go down in an elevator, the opposite happens. The moment you start to move, the elevator drops away from your feet, and for a fraction of a second, you actually feel a little lighter because the floor is moving away from you just a teeny bit because it's accelerating. It'll soon reach traveling velocity and you won't notice it. If you cut the cable, you will feel weightless. If you cut the cable, you will feel weightless. I don't suggest we cut the cable. The reason you feel weightless is because both you and the elevator are falling at the same rate, so there's no pushing up on your feet. There's some examples in the book. There's certainly, if you're puzzled by all this, examples on the internet, and I will attempt to get each of us into an elevator with a bathroom scale so we can actually try it out. So in this drawing on the left, the elevator is going up. You've got gravity pulling you down. That's your weight. That means the floor is exerting a normal force on you, pushing you up. And the elevator, they're showing it as a capital N. And because the elevator is moving up, there's a force on your feet because of that. If you're standing still, gravity is pulling you down, the floor is pushing you up so you don't fall through the floor or elevate. All right, video 1 will stop here. We'll pick up with the rest of the chapter in video 2.